Imagine this, a royal will that isn't just about who gets what. Instead, it's a high-stakes mathematical puzzle. A massive fortune is on the line, and the key is hidden in a room full of lockers. So, let's dive right into this incredible story of Queen Ratnamanjuri and the challenge she left behind.
This is the note that greeted the queen's son, Khoisnam, and his 99 relatives. See, the queen was clever. She knew that if she just handed the fortune to her son, his relatives would pester him for the rest of his life. So she came up with a test of pure logic, a winner-take-all challenge.
So the setup is pretty straightforward. You've got the queen, her smart son Khoisnam, and a fortune in precious stones, or ratnas. But to get his hands on it, Khoisnam has to solve this puzzle involving 100 lockers, all hidden away in a secret room in the mansion.
Okay, so how does this thing actually work? Well, the minister laid out the rules. Each of the 100 relatives, Khoisnam included, gets a number from 1 to 100. Their job is to go into this room with 100 lockers, all of which start out closed, and follow a very, very specific set of instructions.
The key action here is toggling. It's simple. If a locker is open, you close it. If it's closed, you open it. So person 1 walks in and opens all 100 of them. Easy enough. Then, person 2 comes in and toggles every second locker. So they close locker 2, 4, 6, and so on. Then person 3 toggles every third locker. This whole process keeps going all the way up to person 100, who just walks to the end and toggles that final 100th locker.
And that right there is the heart of the puzzle. I mean, with all this opening and closing, it sounds like total chaos, right? But it's not. After all 100 people have had their turn, a very specific set of lockers will be left open. The numbers on those open lockers, that's the code to the fortune.
Now, trying to keep track of every single toggle for 100 lockers would be a complete nightmare. The smart way to crack this, and what Khoisnam realized, is you have to stop thinking about the people and start thinking about the lockers themselves. There has to be an underlying pattern here.
So here's the crucial insight. Every locker starts closed. So, think about it. If a locker gets toggled an odd number of times, it's going to end up open, right? Closed open. Or closed open, closed open. But if it's toggled an even number of times, it'll end up right back where it started, closed. The real question then becomes, what determines how many times a locker gets toggled?
And this little comparison makes it all click. A locker gets toggled by each person whose number is a divisor or a factor of that locker's number. So let's take locker number 12. Who touches it? Person 1, 2, 3, 4, 6, and 12. That's 6 people, an even number of toggles, so it ends up closed. But now look at locker 9. Who touches that one? Person 1, 3, and 9. That's 3 toggles, an odd number, so it ends up open.
So, you see, the real question has nothing to do with lockers at all. It's a pure number theory problem. Which numbers out there have an odd number of divisors? And that leads us to a really special type of number.
Just think about it for a second. Divisors usually come in pairs. For the number 12, you've got the pairs 1 and 12, 2 and 6, 3 and 4. See? That pairing is exactly why most numbers have an even number of divisors. So what would make a number different? What breaks the pattern?
The answer? Perfect squares. For a number like 9, the divisors are 1 and 9. But then you have 3. Normally, 3 would need a partner, but in this case, it pairs with itself. 3 times 3 is 9. That one factor that's its own partner is what gives perfect squares that odd number of divisors. That's the key.
And just like that, Khoisnam had the first part of the puzzle solved. He knew the only lockers left open would be the ones with perfect square numbers. 1, 4, 9, 16, and so on, all the way up to 100. 10 of them in total. But the queen wasn't quite done with him yet.
So inside these 10 open lockers, Khoisnam didn't actually find the treasure. Nope, instead he found one final clue, a second puzzle that would give him the ultimate passcode to the safe.
And this is the final instruction he finds. The passcode isn't about which lockers are open or closed anymore. Now it's about how many times certain lockers were touched. He needs to find the first 5 locker numbers that were toggled exactly 2 times.
So here's the new question. We already know the number of times a locker is touched is the same as its number of divisors. So which numbers have only 2 divisors?
And the answer, of course, is another very special group of numbers, prime numbers. By definition, a prime number can only be divided by 1 and itself, which means it has exactly 2 divisors. At that moment, Khoisnam had everything he needed to finally unlock his family's fortune.
So what's the first locker that was touched exactly twice? Well, it's locker number 2, the very first prime number. That's digit 1 of the code.
Next up, Khoisnam just had to find the second number with only 2 divisors. That, of course, would be the number 3, another prime. The second digit is now in place.
He just keeps the pattern going. The third prime number is 5, which gives him the third piece of the passcode. You can see the code taking shape now, can't you?
The fourth digit he needs comes from locker number 7. He's so close, just one more to go.
And the fifth and final prime number in the sequence is 11. Khoisnam had the full passcode, 2, 3, 5, 7, and 11. Just by understanding these basic, fundamental properties of numbers, he cracked the Queen's puzzle and claimed his inheritance.
What seemed like this totally random game of opening and closing lockers was actually this beautiful display of hidden order. The solution was right there all along, hidden in the basic properties of the numbers themselves.
And that is the real lesson from the Queen's puzzle, isn't it? It wasn't just a test of how well you could calculate things. It was a test of seeing the patterns, the logic that governs our world. It just goes to show you that something that looks incredibly complex can often be solved with one simple, elegant idea.
The Queen's puzzle showed us the secrets hidden inside perfect squares and prime numbers. It really makes you wonder, doesn't it? What other puzzles, what other secret codes are just waiting out there to be discovered, hidden in plain sight, right inside the world of mathematics?